So this gives a different view of GST than what's conventionally in literature. Okay, so the last thing I want to do is wrap this up by coming back to the perovskite ferroelectrics. So this is about piezo crystals. I'm not going to talk about piezo crystals, but it's also something that I learned at this workshop in Williamsburg. And I was on a bus recently with Lane Martin at a conference. And he brought up this subject, we talked about it, and he told me there was a problem with the applications of piezo crystals in transducers, which was a breakdown problem or a failure problem. And I started wondering about that. So what could be the origin of this breakdown problem in transducers? And so one possibility is an electrical type of breakdown. It's just a speculation. And the idea is this, is that this is PMN PT, the phase diagram. In these materials, in contrast to PZT, there's quite a lot of temperature dependence, and this leads to temperature dependence of the dielectric responses as well. That's different than PZT, which when you normally operate it, you're far from temperature dependent boundaries, you're near a morphotropic phase boundary. So the idea was you could have a thermal runaway effect, where when you drive the transducer, if there's a local place where the energy is concentrated, then the temperature will rise, then the dielectric response will rise, and that will concentrate the energy there. And then, of course, it becomes a balance between the rate at which you put energy in and the dissipation of energy through thermal conductivity. And so it becomes a question of thermal conductivity. And so we were thinking about the mechanism in lead telluride for low thermal conductivity, and whether the same kind of explanation held in perovskite ferroelectrics. In other words, that nearness to ferroelectricity gives you low thermal conductivity, which would be an unsolvable problem, or if there's more that's important. And there's more that's important, it turns out. So we looked at two materials that have different behavior. One is potassium tantalate, which is near a ferroelectric transition, kind of analogous to lead telluride. And then we looked also at lead titanate in its tetragonal phase, which is a ferroelectric material. And so here are the phonons and the phonon density of states. The important thing about these is that in potassium tantalate and other B-site driven ferroelectrics, you have unstable modes, but they're concentrated near gamma and along some directions that have been discussed, the chain-like instabilities that have been discussed long ago. But here's the phonon density of states. You see a peak here due to potassium, but otherwise it's regular. Lead titanate, on the other hand, is an A-site driven ferroelectric. And so you have this large peak in the phonon density of states associated with lead off-centering, and it's quite incoherent in the sense of being spread over the chromosome, and you can see different kinds of modes. So at gamma, you can see this blue color, which is indicating positive Grun-Eisen parameter. That's the effect of compression. And then here near the zone boundary, you have these soft tilt-type modes, which have opposite Grun-Eisen parameter. They're enhanced by pressure. So what effect does that have on the thermal conductivity? And it turns out it has a very large effect. Here there's also experimental data to compare with what I'm showing as lines, calculations, and as dots, experimental data. So it was already known that the thermal conductivity of lead titanate is lower than potassium tantalate. And what we did was we did anharmonic phonon calculations using Sheng BTE, which is similar to the phono 3PY code that you heard about earlier, and calculated thermal conductivities from anharmonic force constants. So these are different, and the question is why. And so here is the three-phonon anharmonic scattering phase space, and I mentioned already in the context of lead telluride that not just the gamma point's important. And what you can see is in this region below about 10 terahertz in in lead titanate, this is a log scale, by the way. The scattering phase space is just very, very much larger. And the reason is because of the A-site-driven ferroelectricity, which gives you that soft mode throughout the chromosome, which is very favorable for scattering. And you can see the coincidence between the scattering phase space and the frequency at which the lead-based modes exist. So we have an explanation for why the lead-based materials have low thermal conductivity, which might perhaps be useful in modifying them to improve the thermal conductivity. So I think my time's up, and so I just want to briefly summarize. I gave a bit of a scattershot presentation with several different things in it, and so I just want to remind you of what I spoke about. So the importance of complex band structures in thermoelectrics, if you're interested in thermoelectrics. The nearness to ferroelectricity, which provides dielectric screening, which is important for mobility, and also is a mechanism for low thermal conductivity, which is also desirable in thermoelectrics. Some comments about GST, a little different than conventional wisdom, and then a relationship between lead-based, in other words, A-site-driven ferroelectricity and B-site-driven ferroelectricity, and thermal conductivity, which might be related to some problems with practical applications. So thank you very much.
Time for a couple of questions. Ron?
So I'm kind of asking from ignorance, but so in good thermoelectrics, is the thermal conductivity then from phonons or from the electrons?